Hello, my name is Michael Luciano. I am an EE student at the University of Illinois Chicago, and this is my 491 ECE extra credit project. Right away you'll notice that I'm not using MATLAB, I'm using a program called Octave, and this is a program that I think is based on MATLAB. It has a lot of the same functions and way of using it, um, except it's open source and it's free to download on the internet, so that's why I use it. Anyways, um, right away when you execute my program, it'll give you this prompt saying that this is to help visualize linear, circular, and elliptical polarization for a UPWTM wave. And it gives you the first prompt to choose the direction of propagation in the X, Y, or Z direction. And so right now I'll choose the X direction, and then it will ask you to choose the electric field amplitude in the Y direction. We'll choose 4, and then now in the Z direction we'll choose 3, and then it'll ask you to give a phase difference between the components. We'll choose 0. When you hit enter, these two figures will pop up on the right. You can see the bottom here is a vector diagram showing how the fields change in time, and you see the blue line is the electric field, the black line is a magnetic field, and you can see that kind of traverse as it goes on. Up here we have the E field polarization. We have a linear line because the phase difference was 0, and you have the correct magnitudes in the Y and Z direction. When that is finished, it will disappear, and you will see the prompt in the command window telling you the polarization, which in this case we saw it was linear, and because it was linear it will give you the inclination angle in degrees, which in this case was almost 37 degrees. Cool. So now that you've seen it run once, I will give a little description of my code. So here we go. When the user picks the direction of propagation, they decide which blocks of code it will go through. If they choose X, it goes through this block of code. If they choose Y, it goes through this block of code, and Z, it goes through this block of code. Each block for each direction is very similar, just minor differences in directionality are in place. So for the sake of this presentation, I'm only going to go over one of the directions and just know that the other two are very similar. So right away, I set eta to 120 pi because this is going to be moving in free space. And so when they choose the X direction, they also input the Y component, the Z component, and the phase difference. So when they do that, the phase difference that they input is changed to radians so that I can use it in equations. And right away, the Y component and the Z component are calculated on this X lin space from 0 to 2 pi. And that will give me my graph for the E field polarization in the top right corner. That's where we saw the line earlier. Next, we'll go through this for loop where this t variable is referenced from 0 to 1 in 0.05 increments, and you can see this t variable inputted into the y and z component and from the E field, and the y and z component for the magnetic field, and this is so that you can see the vectors change with time. I chose 0.05 increments so that you get about 20 different pictures, but you can change that if your processor is faster. I only have an i3 processor, so 20 points was kind of pushing the limits here. Anyways, we also chose the X components for both fields to be 0 because that's where the direction of propagation is going. And then now we have our subplots. The first subplot here is the E field polarization curve, and that is pretty simply set up. The next subplot here, this is where we have our vectors. Right away you'll see these axes functions. That just sets the axes scaling so that depending on what amplitudes the user chooses for the components, we'll get a decent graph to see it. And then next we'll see the actual vectors here, here, and here. I used this quiver 3 function that I learned a lot about over the course of this project. The first 3 numbers here, x, y, z, This is your starting point, so I chose the origin for all three of my vectors, and then the next three is the ending point. So for the direction of propagation, I have it in the x direction only. And then the E field, I have EX, EY of t, EZ of t, so that it changes with time, and then also BX, BY, BZ that are functions of these E fields, so they also change with time. And then next, simply we have some titles, labels, and then here is where we set the vector colors. We have the E field is blue, magnetic field is black, direction of propagation is red, and I also had to change the arrowhead size because it was by default way too big. Also, I put some text on the figure so that you can more easily see the direction of propagation, and we also made that text red, and then there's also a legend so that you know what you're looking at. Next, we have an if-else-if statement that lets you know what the polarization is like and what handedness it is, and it just goes through conditions based on the phase difference and amplitudes of the components so that it can correctly identify the polarization of the wave. Okay, so I'm going to show one more demonstration, and then I think you get the gist. Okay, so for this one we're going to choose the Z direction. I'm going to show you a circle, so we're going to choose equal magnitudes on both components, and we'll give a 90-degree phase difference. When I hit enter, you will see the E field polarization curve. It kind of looks like an ellipse, but if you look at the axis, it actually is a circle, 4x4. That's just bad scaling on the figure part. And then on the bottom here, we see the direction of propagation is in the Z direction, this red line, and you can see the magnetic field and E field traverse around it. And when it's done, you'll get a prompt here that says it is left hand circular. Thank you very much for watching this video.